All right, maybe we should get started until the next person comes in. Come on. All right, so welcome everyone to lecture 17 of CS 545, the introduction to robotics. So welcome back from the spring break. So hope it went very well. I spent a lot of it grading the midterm, so that was my spring break. I basically went to a running race, and then after I finished it, back to my hotel, and then did grading. So, all right. So some logistical information. So the regrade requests for the midterm, they're due this Thursday at 11:59 p.m. So I made a post on Piazza with the details. So just look at that, and then if I made a mistake in grading, you should get the points back. So just make sure you look at the grade scope, and then you can see that plus the solution that I made for the midterm as well. So you can just check that. So I see that not everyone has actually seen their grade. Like on Gradescope, I can see who's seen it and who hasn't. So even if you're a PhD student who you don't need, you just need a B minus and then you'll be fine. It's still helpful just to look at the grade and then check it anyway. And then, yeah, when you do the regrade request, just try to make sure that you explain why I made a mistake grading, because I mean, it can happen. So the worst kind of regrade request is basically like, I was in a hurry, I meant to say this, can you give me extra points? Like that's not really an effective regrade request. So the most effective one is, you can see that I said this, which matches the answer, but I didn't get full credit. Like that's the most effective regrade request. So try to make sure you get it done by this Thursday evening. So, if you come to me Friday with requests, then I don't really know what else to say because it'll be due on Thursday night. So hope it goes okay. Yep, and then hopefully that will also give you some practice for the final exam. So part of the practice for the final will be like you can retake the midterm, and then you can get a feel for the kind of question that I tend to ask. And homework 3 has been released and due April 1st. Lab 3 has also been released, so it's due a little bit later because there's a physical robotics component. So hopefully that answers a bunch of questions that I know a lot of you have asked about the lab meeting time or like the lab time. But so it turns out that we don't actually use the Tuesday 4 to 5:50 time. So I'm not sure why the course asked me to give a lab time. What we're really going to do is just give you like 3 days, and then you can pick which one works best for your group. Yeah, any logistical questions? Yeah. Oh, yeah. So what will the final exam be cumulative? So the short answer is yes, but it's going to have more emphasis on the second half of the course. But it will be, I mean, it will be cumulative because like I can't just pretend to ignore the first half of the course. Yeah. And yeah, I think the difficulty wise, it'll be roughly the same, but like the way I do it, the exams tend to be hard, but like I try not to make the threshold to get a good grade very high. So I try to lower it just to be fair to people. So yeah. Yeah. Anything else? Any logistical thing from the people just coming in? All right. Yep, so let's get on with the technical portion for today. So today we're going to be talking about motion planning, and then the same thing for Wednesday. So motion planning is a very fundamental topic in robotics. So I hope that this lecture and the next one will be very useful. Yeah, so like just to give a step back, what is motion planning? Well, let's just look at what's going on in the video here. So you have some kind of robot. It had you can see it had the Carnegie Mellon logo there, where I did my postdoc. So it must be a good robot, I guess. So you have a robot here that did some like grafting and then deposited something. Yeah. But the exact thing that the robot is doing isn't that critical, more as, it's the fact that there's a way that we can do this at all. And motion planning is the way that we can try to formalize, how do we get robots to effectively do things? Like, how do we get a robot from like this configuration to another configuration? That kind of thing is basically done with motion planning. Even if sometimes the decision making, like maybe there's a hand-coded, a human who decides go to this code or a machine learning algorithm that said the same thing, you end up converting them to some kind of underlying like motion planner that actually moves the robot for you. So, and then of course you can do other things like assistive feeding, where the motion planning now has to plan, the robot is at this pose with some joint angles, and then figure out a plan to get from the initialization to the pose that brings the I guess the food to the patient, subject to, well, I guess like what would you be like? What do you think like subject to should be here? Yeah, depending on the kind of restraint. So you probably want some like joint angle limits on how fast the robot can move. If it, especially if it's operating around human. Hi. So what kind of motion planning problems are there? Well, there are many different variants. So the plan could be maybe discrete, continuous, or hybrid. We're going to cover that a little bit more Wednesday's class. The environment itself could be immovable. There could be moving object in there. There could be, object that the robot can move. So, generally speaking, the more dynamic things are, the more challenging it is because you have to keep reacting, and then the motion planner has to consider that. Then there are different types of interaction that could be there. Like you could just have the robot operating in free space. You could also have it trying to touch and pick and place different objects. You could also have it operating in some really cluttered situation like a closet where, the robot has to do something, but at the same time, it's going to making contact with a whole bunch of other things that are, you know, surrounding the robot. Then in terms of uncertainty, so we talk a lot about like state estimation. So think of X as like the state of the robot, or maybe if you want X to be the robot and the environment, then you can use that as well. So like if there's no uncertainty, which usually only happens in the most trivial cases, then you can just think of it as, you have X. If you have other types of uncertainty, you might just assume, well, let's parameterize it with some distribution, or let's just pretend that we don't even know anything about it. So, and then, static and dynamic, that distinction is mostly if the motion planner has to consider things like not only Q, but Q dot them. So everyone knows the Q dot notation, right? I think we've used it before. It's like a velocity thing. So they have like the joint angle position and the joint angle velocity. All right. So a standard motion planning problem would be like this. You have the world in R2 or R3, right? You have some kind of obstacle. So in this visual here, the obstacles are going to be these circles, right? And then the world is going to be a 2D point. Why? Because it's easier to describe in a PowerPoint presentation. You have a robot and it's configuration based, right? So again, because we want to simplify the presentation, we're going to assume that a robot is a single point mass. So it's like a single dot. Yeah. I mean, in practice, robots aren't like that, but you can still approximate a robot center with a 2D coordinate, especially if it's a mobile robot. And then, how do you deal with the obstacles? You can just pretend that the obstacles are bigger to account for the fact that the robot itself is not a single point mass. And then you remember from before spring break, we talked about what is a configuration, right? So it's a complete specification of the position of every point on the robot. So again, the robot is a point math, so a single point is all we need to know. And yeah, we talked about the difference between free space and optical. So Q is like the whole set of possible spaces. Here is like a bounded 2D plane. And then Q obs are like any points that are in the two optical. And then Q free is like anything in the configuration space that the robot could be at. And then you have some kind of start and goal configuration. Sometimes you'll see Q init and Q goal, but as long as you know which one's the start and then the end, it should be fine. And the objective here is compute a path from this function tau from 0 to 1. The only reason for 0 to 1 is to make it, you have some arbitrary time interval, just scale it to 0, 1. Yeah, that's all it really means. Yep, and then compute a path so that your starting configuration is at the beginning and then the goal is at the end. Yeah. And then in practice, when you're coding it up, you'll probably discretize it. Like you'll probably pick 100 different waypoints and then have the robot, go to each waypoint or something like that. Yeah. So today, and whenever you read references, they'll usually describe motion planning in 2D. But the general principle applies even if you're dealing with like 7 degrees of freedom arm, where you just have to think of these as applying in 7D spaces instead of like 2D. All right, so we're going to talk about roadmap. So when we talk about roadmap, that'll give, well, I guess you can kind of know what it means by the word like roadmap. So it's basically a map that tells you, there's a bunch of different nodes on it, and then paths that can go from one node to another. And so it's actually pretty interesting. Some of the robotics textbooks, they actually use the LA freeway system as an example roadmap. It's too bad they can't use the metro because the metro is not as dense, which is unfortunate, but whatever. So for a roadmap, you can construct a network of, in this case, it's highways. More generally, just think of them as a path. You store the network as some data structure. And then if you want to go from a start pose to an end pose, then you just include them as part of the roadmap and then run some kind of graph search algorithm, and then you get your path. Assuming one exists. And the nice thing is if you store this as a roadmap, then you can reuse it. So it's not just for one query, you can have this roadmap, but then you can query many different starting and ending poses. Yeah. So what we're covering today is actually a multi-query planner. Then Wednesday, we cover single query planner, where it's mostly designed to be queried once. All right. So here's one example of a roadmap style algorithm. So this is called a cell decomposition. So you can see the reference here if you want to find more about the source, but I'll just describe what it's showing now. So you have some kind of space into, like the objective here is you have some free space and you want to divide it into a set of regions, which you call cell. Now, if you look at what's going on here, these are representing obstacles. So generally speaking, anytime you have a shaded area in some white background, those are obstacles where the robot cannot go. And again, we're assuming 2D point math robot, just to make everything simple. Now, what vertical cell decomposition does is you'll have some set of vertices where you can sample them using whatever procedure you want. Then you try to extend rays like up and down until you hit obstacle or the boundary of the workspace. So like if you have a point here at this corner, you can extend it upward and downward. If you have a point here, you can only extend it up because you cannot go down. Yeah. And same thing here. If you're here, you can only extend down instead of up. And if you're here, you cannot go up or down. So again, the reason why we're only considering up and down is because it's called vertical cell decomposition. You can use different variants of cell decomposition that if you want other direction. All right, so here's an example. So you have some optical, and what we're going to do is we're going to try to sample different points and then basically extend them up and down. So imagine you sample something here. Maybe it's like at the bottom of this optical region. The exact procedure you can just specify using whatever method. So here you can go up and down. Here, you can do the same thing here so imagine your starting point is like at this corner. You can go down and then you can go up. Or, think of it as just being like right at the border. Yeah. It's a little bit, it's not exactly drawn to scale, but just pretend that it is. It's like off by a pixel. Now, if you repeat the process and you try to say, let's say you try to sample different points along the x-axis. And if we're over here, then we'll only draw a line from here to here. If we're here, then it'll be like here to here and so on. Yeah. So again, this is just like an informal description, basically meant to show like intuitively how the thing works. So the exact locations of the line segments, they could be different depending on where you decided to sample your point in the configuration space. All right, and then what happens? So this thing will only produce what you call like one cell and two cells. So a one cell is like a vertical line segment, and a two cell is like a trapezoid or a triangle. So here you have some triangle, here's another trapezoid, and then here's another trapezoid. Are there any other shapes? No, I gave it away here. So yeah. Nope. All right. So what do we do after this then? So for every cell I, you can select a point at it, which for this example, let's assume that we will use centroid as our point for each cell. So for every line segment, we will pick the center of it. For every trapezoid, we will pick the centroid of it, which I guess it's also, you can also call it a center point. And the way this will look like, it'll look roughly like this. So for this diagram, what we did is for every triangle and trapezoid, you add in a black dot. Now it's supposed to be the centroid. So you can just think of it as, you take all the points in it, then you average it, and then that's your centroid. So for example, you have this centroid for this triangle, you have this one for this trapezoid, and so on. Yeah, so we got them all here. Then after that, we will also put in the centroid for each line segment. The way that will look like is this. You have, for this line, you pick the center here. For this line, it's really split into the region above and below the optical. So you get a point here and a point here. And then, yeah, the same thing if you proceed to other lines, like if you consider this one, you get a centroid here and here. All right. Is that all clear? Did we miss any point? I don't think so. So once you have all these points, then you can build a graph, right? So you'll see that a lot of these roadmap algorithms, they end up building some kind of graph, right? So this is just how do you build a graph from this particular case. So the way that we do it here is, for every centroid that's in a trapezoid, you try to, or a trapezoid or a triangle, you connect it to all the one cell points that are like, adjacent to it or part of it. So the way that this will work is, so let's look at this. Let's look at like, this point this point at the far right here, how many line segments will we form in the graph that connect, that point? Yeah, because we have to make a graph somehow. So how many neighbors will we have in the graph, basically? This one here. One? Yeah, so it's one, right? So this one only has one, right? Yeah, because the way that by construction, we're just looking at all the centroids and then connecting to all the line segments that have a center point that are like adjacent or part of the triangle or trapezoid. All right. But what did we just make here? What is this graph? Like when you look at this graph, what do you think it should do? Like how can we use this graph? Sorry, what would you say? What about possible path? Yeah, so it's a possible path to navigate through obstacles. Yeah, sure. Yeah, that makes sense because yeah, if you look at how it is structured, it doesn't intersect any obstacle. So you can go from like one node to another, right? You can use your favorite graph search algorithm or traversal algorithm. All right, we have QS and QG. So this is the same graph as earlier. I just zoomed in a little bit. So if you have QS here, which is the start, and then QG, which is the goal, then it seemed like we can just connect QS to one of the nearby node, QG to another nearby node, and then we just run a graph traversal algorithm. Yeah. Yeah. So once you have the graph, you don't need the cell information for planning. Then given a query, you find the start and goal cell point, and then you connect a path. And so here we just chose to connect the start to to this vertex, but it could be like this one. You can just run a nearby like k nearest neighbor search to find the nearest point, and then you pick one of them, subject to some criteria that you might pick. All right. So any questions on the vertical cell decomposition before we move on to another similar example? Yeah.
I see there were several cycles in this graph. So how to know decide which direction actually?
All right, so there's a couple of cycles in the graph. How do you decide which path to take? I think that's more of a question of what graph search algorithm you want to run. I think that's a separate question from you'll probably have some graph traversal algorithm in a library that you can run, and then it'll probably pick that for you. I mean, it's not. Yeah, I think just think of it as you're going to offload it to your graph traversal algorithm. Like that's the way I think of it. Yeah, question?
What is the boundary? There's no boundaries.
All right, so what do you do if there's no boundary here? There's infinite space. In practice, do you get infinite space? I mean, in a warehouse, there's always going to be some like walls, right? So I assume in most practical cases, there's going to be some kind of a boundary. In practice, you could just decide, well, even if you have infinite space, let's just pretend that we're going to put boundaries somewhere. But yeah, there should be boundaries somewhere here. All right. All right, so visibility graph. So this is another like way to do like a roadmap style planning. It's a slightly different approach, but it's also one that had different pros and cons depending on your situation. So let's suppose that we have these opticals. So there's one like rectangle, and then there's a triangle. What you can do is you can form a visibility graph by taking all the vertices that are part of these shapes, and then you try to connect them to any that are visible from it. So you're going from all the vertices of one shape and then checking can it reach the other one. By visibility, we mean a straight line. It doesn't have to be a straight line, but that's usually the one that makes the most sense, like I think. So if you look at this vertex here, if you try to make a straight line path to any of the vertices of the triangle, there's nothing because the shape itself blocks it. But if you have like this one, then this point can see the top vertex of the triangle and then the left one for the triangle too. Then this one can see the same too. So you add in the line segment to connect the point. And then at this point, if you look at this, we've already gotten some kind of graph, right? It already looks like some kind of graph or roadmap. You have your starting pose and then the goal pose. So again, anything we're going to look at, it's going to be, we're going to think about connecting your starting and then the ending, point. Now, what happens here is you can still do a similar visibility check for your starting point and then your ending point. So for your starting point, you can do a similar, check, can it see any of the vertices of either shape? Same thing for the goal. So what might happen here is you have your starting point here, and then it connects to this one, and then this one. The goal point could connect to, it could actually connect to all three of the vertices of the triangle, and then it can connect to, this vertex up here. What do we do now? Can we use it? Can we use this already for planning? Yeah, right. So so I put in the, there's like a red set of lines here, then you can always, yeah, because we've already made a graph and then you can still like traverse it. Yeah. Does anyone see an issue with this path? Yeah, the back.
There's no offset, so it's very close to offset.
Um, so yeah, there's no offset, so you're very close to the optical, right? And in practice, I was emphasizing a lot in the first half of the course that if you claim to me that your robot is noiseless, and then you always go in a, like if you go to a pose, robots are not going to be noiseless, like they're going to go to the pose plus or minus some kind of errors in the position, especially mobile robots. I found are very, they're very noisy. And then if the opticals are something like really dangerous thing that shouldn't be touched at all, then you probably need some kind of buffer zone to protect against that. Yeah. So how do you make sure that the robot does not touch the optical? Then we kind of already covered it earlier in an earlier class, but you can just make your optical bigger. So depending on the shape of the robot, like if it's some circle in 2D, you can just expand each optical by that radius, and then you end up taking into account the robot's shape, and then you can increase that radius further to pretend that you get to enforce an even bigger offset. Yeah, so when you're designing robots for motion planning and practice, these are the kind of technical considerations that you'll have to do. Like, how much tolerance do you want to be how much do you want to be close to the optical? Uh, yeah. All right. So we talked about two methods roughly. So it's like the vertical cell decomposition and the visibility graph. So what we did here is we kind of assumed that we had an explicit representation of the geometry of the configuration space. So we like knew completely what the shape of the opticals were. Now, in practical cases, when you're planning in more complicated spaces, then this kind of geometric reasoning gets a lot more complicated. So what researchers have done a lot is they focus more on sampling-based planning, which does not require that kind of explicit geometric representation. So an example, like this example is from one of the references in the textbook, and then they claim that this is like a planar robot, but it has multiple degrees of freedom, and when they're trying to make a plan to get it to like encompass this thing, it gets hard to do that with explicitly representing the geometry. But when they're doing sampling-based planning, like the probabilistic roadmap planning that we'll talk about next, then it becomes a lot more feasible. So it is somewhat surprising, but the simple sampling-based planning methods have worked very well in practice. So, if you're actually working with robots, you'll probably at some point be using algorithm like probabilistic roadmap or rapidly exploring random tree. With that one we'll cover next class. All right, so that brings us to the probabilistic roadmap planner. So this algorithm consists of two phases. The first is a pre-processing phase where we construct the roadmap. The second one is a query phase. So we search it to try to find a path from the start to the end. So again, it's very similar to the two things that we were covering earlier, just that the way we construct the roadmap is a little bit different. And it's also, I would argue, a lot simpler. So it did not attempt to explicitly construct the boundaries of those, configuration space optical. The only thing it really needs is a simple collision checker. You have your robot configuration. Is it colliding with some optical or not? Or like if you have two sets of configuration and you try to go from the start to the finish, where it's a very local connection, then can you do that? Basically, all you need is you basically need those two ingredients, like a very good local planner that can move the robot a small amount, and then a collision checker. And collision checking is at a very high level. It's a separate module, but it's also very, these days it's very reliable. And it's also very fast to do. So, which is good for the purpose of this algorithm. And if you're using different robots, then you can also tailor them to specific robots and application. Like there are some robots that maybe they have padded, arm or whatever, then you can change the collision detector to be a little bit more, flexible in those cases. It's stuff like that you can always incorporate depending on your specific robot or your specific need and whatever. So like this is a very, broad thing which incorporates collision checking as a module. Yeah. And the way that we will describe it is we're kind of describing it today as a single query planner because we will just have a single query go from the start to the finish. But in general, we will do that multiple times. So if you're only going to be doing like a single query, then you might not do this. You might just do the stuff we'll cover on Wednesday. But if you have to repeat and reuse this roadmap a lot, then you can use something like this today. Again, depends on your specific need and what robot you're working with, how you're using the robot, and so on. All right. So how do you construct the roadmap? So again, think of the robot as a point, and then you have these two optical. You sample a bunch of points. Again, these are all points in the configuration phase of the robot. If you no, if you want to think of them in higher dimension, then think of each point as representing some kind of higher dimensional configuration vector. But for now, just think of it as a 2D thing because it's much easier to describe. All right. So then the question is like, how do you connect? How do you, make a roadmap from? So for every point here, you can pick a point at random or whatever, and then with some pre-specified value of a radius, just search for all the points that are within this distance to that point. And then if they're within that distance, you connect them with an edge. Right? So if you were considering this point with the radius of the circle that we covered last slide, then you'll connect these two edges. You'll make these two edges to connect those points. And then you can repeat that process to get something that looks like this. Right? So if you notice the main difference between this and what we covered earlier is that there's no notion of, we pick some vertices of these obstacles and then we try to connect them. No, we didn't do that here. We also didn't do any vertical cell decomposition thing. It's just, again, it's really simple. If you're programming it, you just run, numpy.random or whatever, right? And then you get a whole bunch of points. All right, and then we have your start and then the goal points. Yeah, question?
Go over how we connect the points again, once.
Oh, so this is what happened when you connect one. If you can iterate through all the points in the set of sample points. You have some radius value or some distance hyperparameter. You can pick that distance, but ideally should be big enough that like you can connect some points together. Yeah. So if it's within this distance, then for this point, you get all the points that are within some distance of it, and then if they're within it, you connect them. And then just iterate through all the points that we have. Yeah. Yeah.
Could you give some intuition as to how that would avoid obstacles? Like how that would actually avoid obstacles and how we actually pick the value for the radius?
Oh, okay. So how do you avoid obstacles and then how do you pick the value of the radius, right? I think for the value of the radius or the distance, I think that's something you're gonna have to pick. If you're running some off-the-shelf algorithm, maybe they've given you a default value, but then you can pick. It probably should be something that keeps it probably should keep the degree of each vertex not too big. I guess like you probably want you don't want the graph to be too complicated. At the same time, you also need some edges to connect any point to another. Now, if you're talking about optical, then the construction of this assumes that you have some kind of local motion plan. And by local, I mean something that really only works for very small changes in the configuration of the robot. So a local planner would be something that can check if the straight line between 2 points has an optical in front of it. So there's no it's not a good example here, I guess, but if you imagine this point was like up here, and then you try to connect it with the one over here, the local motion planner should be able to prevent that edge from happening. So we're going to talk a little bit more about that local motion planner, but just think of it as it is something that you do have to assume, but it only has to work if you're considering very small changes in the configuration of the robot. Yeah. Yeah.
But the points that we're sampling is there a possibility that one of those points would lie on the obstacle, or are we sampling from the so-called free space? But then also we don't quite have an idea of the geometric proportion of the object, so how would we decide that's free? Sorry, it's a vicious cycle in my head right now.
Yeah, so one of the things that we're going to assume is that you have a procedure to detect whether a given robot configuration is colliding with obstacles or not. So you kind of need that assumption, which is usually a weak assumption, I guess. So you can, if you're dealing with a plane, you just sample points, at random using your favorite random number generator, then you run the collision checker. Then if it's in collision, you just ignore it. Yeah, basically. You might need more sophisticated sampling procedure for some cases. We'll talk about that. Yeah. Yeah. So yeah, I think you know what's going to happen now. Like you have your start point, and then you have your goal point, right? And then you just find the node that's nearby in the graph, and then you connect it to them, connect it to it. And then you run your graph traversal algorithm on it. All right. Oh, okay. So this is the algorithm that, at least in one of the readings for today. So again, this is how you do the roadmap construction. It's not querying. So again, there's the phase one, which is you construct the roadmap. And then phase two, you actually query it. Yeah, so that's what I mean by here. So the delta thing here is the local planner, right? That returned a collision-free path if it exists, or they use nil if it fails, right? Again, the local planner is only designed to work for like local cases, because if it was good enough to work for arbitrary configuration, it would give you all you needed, right? Yeah. So again, the assumption here is that this thing only works when your configurations are really close to each other. Yeah. And then your distance is often Euclidean. I guess that's often the default that people use. You can pick a different distance if you feel like you need to. Yeah, then you can kind of see what's going on here, right? You make your graph, and then you start with nothing for your vertices and edges, and then you have a random configuration and your configuration space. Repeat until it's collision free. So, and then for every vertex, vertex, which is the same as for every configuration here, you find the k closest neighbor chosen according to distance. And then if there's no edge and the planner is not nil, so you get a plan, then just add the edge. Yeah. All right. So how do you query it? Well, the most basic approach would be for your start and then a goal configuration. Consider the k closest node in the roadmap. Try to connect any of them with the local planner until one succeeds, and then you've gotten your graph. And then you can find the shortest path between your start and then the end. So what we describe is the most basic way to do this. So if you're reading this and you're thinking, well, this could be a lot better, then there's many ways to customize. So, this is the most basic version that, people developed in the 80s and the 90s. And then, these days, by now, you've got a lot of variants that could work depending on, they make different assumptions about what problem you're dealing with, basically. All right. So what about the limitation? What about this? How do you fix this? Sample more points, right? Yeah. Sample more points. What about this? It's called the narrow passage problem, for obvious reason, so. Yeah, we can sample more points, sure, you can do that, but. Is random sampling gonna uniform sampling, will that work? Yeah,
I was just gonna say, maybe like tweak the radius parameter,
to change what parameter?
the radius that we're talking about.
I don't know about that, because if you have this point here, and then you have another point, like even if the radius were really long, like this point cannot reach this point, well, pretend that the narrow passage is super tiny that, this point cannot see this one. Yeah. And no matter if you increase the radius, it's still gonna, like this passage is still gonna block. Yeah. Yeah, yeah.
If you can combine that with, I was going to talk about this. Yeah, just divide the whole graph into several parts and do the random sampling at a certain point, so that we can assure that as long as the whole graph is connected, we can definitely find the pathways.
So it seemed like you suggest some, like, I think you're talking about the visibility, the example earlier where we talk about the vertices of the optical, then you can sample from those and then include them as part of your graph. And then, yeah, maybe that'll help. Yeah, that's one way. I think what you're describing is number 2 here, right? Sample near optical. Yeah, basically. So yeah, again, there's many sampling strategies. So the thing that whenever you read stuff about the algorithm, they make the claim that unless your planning is very pathological, then even naive sampling often works. These algorithms are so simple, but they're so effective for stuff that seems very simple. Like that's a high level takeaway. Yeah. Yeah, then yeah, you can sample, like if you're trying to sample like values for a rigid body, for example, you can sample from an interval of allowed values. Yeah, for rotation, just be careful that you're not, just be careful about sampling rotation and thinking about, at this point, like what is the distance between two rotations? Because you got to wrap around like 359 degrees to close to 0 degrees. So just watch out for stuff like that. Oh yeah, so we talked about, sampling near optical, so that could help. There's also a concept of manipulability-based sampling, which means you try to sample more poses in region where a robot might be at singularity. So if you remember last class, we talked about the inverse kinematics and the robot being at singularity, where it can be hard to enforce. It can be hard for the robot to move in certain ways and to enforce certain velocities in a certain direction when it's at singularity. And because of that more restricted range of motion, maybe we want to sample more points near there so the robot can like find some way like out of the singularity. And then visibility-based probabilistic roadmap planner. So we will talk about this. Yeah, I guess for a lot of this lecture, we'll go through an example. If you printed the lecture notes, you probably have seen it. So yeah. So any questions on this before we go into like visibility-based PRM? Yeah.
You sample more singularities. Would that make the robot prefer to go for singularities?
Well, all right, so if you sample more configuration near the singularity, will that cause the robot to go to those points more often? Yeah, maybe you can argue that. I guess the bigger issue is if the robot is at a singularity, but we want it to be somewhere that's not a singularity, it's got to find some way out, basically. So we basically have no choice but to sample a lot and then hope that the graph search algorithm will lead us there.
So you would only really do that if you're already at.
Yeah. Yeah, I think that's probably the most logical place where that could happen. But the reason why this actually does happen a lot is because many times in robotics, we do need robots that operate in like tightly constrained environments. So if you imagine, robot that's, I guess trying to feed someone, and then, they have to be very constrained in where their joint can be. And then depending on how that happens, they might be forced into some singularity, opposed near a singularity. Yeah. All right. All right. So again, the narrow passage problem. So I guess the motivation of visibility-based probabilistic roadmap is that if we have this narrow passage problem, then if you naively sample configuration of the robot and you try to connect them, in order to find a path from the left to the right, you might have to sample a lot of points. And then if the objective is really to traverse it, then sampling all the points might be a little bit wasteful. No. So the objective here is, can you get something like this, but where you have to store fewer nodes? So it's really about, like, I guess, the data structure of how many nodes that you're supposed to be storing that we consider with the visibility-based PRM. Yeah. So the insight here that we use the notion of visibility to cover the free space, but to keep the size of the roadmap small. So you only add Q to the roadmap under these two conditions. It cannot be connected to any existing node, or it connects at least two existing components that are like different components. And the contrast with the vanilla-based PRM is that this node will keep rejecting a lot of samples. PRM will accept like all the samples that are not like in collision with an optical. So this is a much stricter criteria about which node to sample. But the end result of that, at the end, your roadmap is very sparse. And if you use it a lot and you need to store it a lot, maybe that's the trade-off you prefer. So yeah, this is like the insight here. Like this has a lot of nodes and it could be inefficient. This one has fewer nodes where there's one node for each of the two components. Now here, there's no narrow passage, but just think of this as a high level idea. No. Yeah. Then the trade-off here, well, it is more expensive to generate node. Like if you're doing the visibility-based PRM, you may have to spend a lot of time rejecting node and then checking if it's visible with another one. Yeah. But at the same time, when you actually try to connect them afterward, then it becomes simpler because there's fewer nodes to consider for connection. And whenever you connect to node, you have to run your collision checker. Again, I mean, collision checking is generally fast, but there's a limit if you have to run it, billions of times. So to understand this algorithm, like we first will talk about what it means to be visible in some sense. So the way this algorithm works is you can think of there being two types of vertices. A guard vertex cannot see other guards. Yeah. And a connector must see at least two guards. I think they picked the terminology from like security, like maybe you want the guard to be like spaced out where they can see everything. You know, I think that's the history behind whoever picked the terms here. So if you see, if you see Q, like you have Q here, BQ is the visibility region of the node Q, right? And then, this region is the area where, that node can like see everything, right? And what happens here is at the end, you might get something like this, where the black node are your guard, and then the connectors are shown in white. So the connectors connect to guard, and then the guard, you know, have two at least one connector at the neighbor. All right. Yeah. So does everyone see like the potential issue that it depends on where the guard were selected? Like, so if you sample a node at the beginning, you know, that node is going to be some guard. But maybe it's actually not at a very efficient location, in the sense that, you know, given some 2D space with obstacles, you can pick your guard to be a very inefficient configuration. Or you can pick them a very efficient one that like maximally, you know, cover the region. Yeah. All right, any questions on this? I think this is a good time for a break, and then we'll go through like a short, I guess not really a short example, but going through a detailed example of, yeah, how it looks. Yeah, if you're looking at the printed copy, there's a lot of repeated slides that show the steps. So yeah, feel free to take a 5-minute break, and then we'll be back at 5:02 or 5:03. Oh, hi.
What? Right? Actually, if we just want to avoid the collision of borders like that, we can just start from one source sample and then enhance a certain part which is fine, maybe impossible to have an output.
I think what you're describing a different sampling strategy. Yeah, so there's a ton of different sampling strategies. So the only reason why I mentioned the uniform like sampling is because it's the most basic one. Basically, no, at least for class, we just talk about the most basic way to do them. There's always going to be more sophisticated sampling procedures. Yeah.
Good question. So, according to the algorithm we talked about till now, we can just find a certain pathway. But how can we decide whether it is the best or a better pathway?
Better path. So this is an answer for your graph traversal algorithm. So there's a lot of algorithms for finding shortest path. And you know, like there's like textured algorithm.
Yeah.
That you can just run that. Basically.
But on slide 26, the way we connect different points is not unique. Depends on which point we start and how red is. Yeah. So there's so many possible. Actually, the roadmap would be if we start from different point and choose different parameters as the radius. So at this point, how can we decide which of the? But is there a better way to connect all the points?
Yeah, you can do post process. So given your path, you can like post process it to get a more efficient one. So the way to think about it, there's a ton of variables there's a lot of different tools that you can use to improve it. So one of them is like post processing. So given a path, run some other graph algorithm to improve it.
So we talk about today just the most simple one. So there's still tons of algorithm or ways for me to make it better, right? Yeah.
Basically.
Yeah. Thank you.
Again, the reason for this is just like this is the simplest to talk about. Yeah.
Quick question about Aikido. The Aikido, yeah.
It's just a point about I know very little about
It's just for it's just about installation. I can also ask Steve, but do we can we use it with dual booting, or do we need to set up the VM part for that? Like, are there dependencies
Oh,
in the image?
What have you been doing for the earlier lab?
I just have Ubuntu on my laptop.
Yeah, if you just have one, we should be fine.
I just downloaded Captain Workspace.
Pretty sure.
Okay, okay,
Yeah.
sounds good, thank you.
Basically, if you only have one, two, on your laptop, it's probably.
Yeah, okay. Yeah, sounds good. Thanks.
All right, so this is an example of how to use the visibility-based probabilistic roadmap. So remember the main idea here. We want to find a set of vertices here that will let us form some kind of roadmap, but where we want to do it very efficiently so that we can divide it up into these nodes are guard, these are connectors. There's other like guards or connectors. That's it. And then that will give us a very efficient roadmap in the sense that we don't need very many vertices. Of course, the trade-off is no, your vertices might not be a good location. So again, algorithms have trade-offs. All right. So let's go through the steps. All right. Before we even get to this, we set the guard to be the empty set, the connection to be empty, and then this is like some kind of like number of tries. So M is some kind of hyperparameter, like the max number of tries that you can get. I mean, you can't run the algorithm forever. So. All right, select a random free configuration queue. That's the thing. Is that going to be a guard, a connector, or neither? What's that node going to be? Yeah. Yeah, sure. I mean, why not? I mean, you have to start somewhere, right? You need some kind of guard, you know. And the point of the connector is to connect to guard, but you can't do that if you don't have any guard to connect in the first place. So how does it work? So select a random free configuration queue. For all components of the guard, do. How many components were there? There's nothing. So yeah, so we selected a random free configuration. These are empty for all components, but there's nothing there. So you skip this for loop. You go down here. Yeah. If G viz is the empty set, yeah, because we just set it up here. So this is the empty set, right? So we just skip this for loop. If this is empty, you add the guard, you add it to the guard. So this node is like your guard. It can see everything in the shaded area. Yeah. So this is like, your security guard that can see a whole bunch of different things. So. All right, that's the first node. Select a random free configuration queue. We have this one. What's going to happen? Think about it for a bit, and then think about what this node is going to be. Yeah. Or if you already know, you can just let me know. Yeah. What?
Should it be another guard because a connector is supposed to connect two guards at least, right?
All right. So another guard. Maybe. Yeah. If I'm managing a bunch of security guards that are trying to guard this area, I kind of feel like I would want this guard to be like somewhere here intuitively, because like this guard can see this region, and then another guard here could see like this other area. So that is my intuition on thinking about this, but let's go through the algorithm. Select a random free configuration queue. That's what we picked. You're going to set gbiz and capital Gbiz to be the empty set. All right. For all components of guard. Now, this time we already added a guard from the last time. So there's one guard. For all components of guard. When we talk about component, that's basically like the shaded area. Found is false. For all node G of GI, right? So GI is like a component of the guard, and node G of GI, that's referring to this node, right? So this node, like this node is like for this for loop. So for this node for this guard node, does Q belong to the visible region of that node? So you have this node and visible from this black node. So that's the guard. This is visible. So found is true, is found. If this is empty, then you set gbiz to be G, and then capital Gbiz to be GI. So GI is the shaded component. Like that's the shaded component here. All right. So we are going through the if case. Now it's an if and else, so we skip this thing, right? And then we go back to this for loop, but we've already gone through all the guards, so we just exit. And the same thing for, this is only one, there's basically only one component here. Or if you want to interpret it as like three separate components, you can also do that. For this example, it doesn't really change things. So then you go to this, and then if gbiz is the empty set, then it's the guard node. But it's not, because we already, we went through this, right? We went through if gbiz is the empty set, then it's not empty. Nope. So we failed to create a new guard because Q is visible, and it's visible from only one component. Yeah. So again, like if you want to go through the steps again, it would be, you sample this for all the components. This shaded area is the component. If Q belongs to the visible region, which it does, then you make it found is true, then you make this non-empty, because this represents like a number of guards that can see it. Yeah. All right. So this is a very formal way of doing it, but you can also kind of think about how it would work. So if the node is already visible by just one thing, then you just ignore it. All right, select another random free configuration Q. What's going to happen to this node? Final exam question. Guard connector, neither.
Be a guard. Because it's not in the visible region.
Let's go through it. Yeah. All right, we selected this random free configuration. We set gviz to be the empty set. Same thing, yeah, same thing for capital G. I keep saying G, but you know, I guess G and then capital G. All right, for all the components, GI of guard, then you set found to be false. Oh, sorry. I guess I didn't show all the steps here, but for all the node G of GI, this is the only node that we have. If this thing belongs to the visible region of this guard, then you set found to be true, then you do all this. But the problem is that this node is never visible from this one. So this whole for loop just doesn't do anything. And because this is empty, it's a guard. All right. All right, another node. What's going to happen? It's going to be a guard, right? Yeah.
It is going to be connected because two of the guards can see the point, but yeah, it's being covered in.
Yeah, so you think it's going to be a connector? I said it was going to be a guard. Let's see who's right. Select your random free configuration. We've already picked it. This is empty. For all the components of guard. So here we basically now have like, we basically have, you know, two different components from the two different guards. Found is false for all the node G of the, I guess the first component, which is going to be this one. You set found to be true. If gviz is empty, then you're going to assign stuff to it. So here we're going to consider the first guard node. Yeah. So the first time that we're at this if statement, now we're going to go back, right? So we're going to go back to the other component, which also had one node. Onto the second guard node. Let's say this is the second one. This node is in the visible region of this one. Yes, it is. But this thing is not empty because we already assigned to it the prior time. The prior time we went into the for loop. So we have add Q to connection, create edges QG and QG biz. Yeah. And then you can merge components together, but like you kind of get what's going to happen here, right? You know. Yeah, you create edges here. You merge the component. What that does is you basically have, you know, some different region based on, you know, this region was visible from this node, but it's also visible from this one. So I think that's what's supposed to happen here when you merge the two components. And then you merge them, and then when you're at here, we've already assigned to this, so it's not a guard. Yeah. Yeah, so that was, I was deliberately trying to see if someone would correct me. So, yeah. All right. Here's another free configuration. What's it gonna be? Take about like 10 seconds to think about it. I think it's gonna be a guard. Right? No? But what do you think it's gonna be? I think it's gonna be a guard. We'll see who's right. No one wants to say anything. What do you think it's gonna be? Let's see what it does. No, we have selected this. We have selected this configuration. This is set to be empty for all the components of guard. So I believe, no, the component is now this combined gray shaded area. Oh yeah, so it's only visible by one guard. So we reject it. Yeah. Right. Yeah, because for all components, I mean, if you want to go through it in more detail, it's like for all the components, there's basically one component. For all the node, the only guard that saw it was this one, right? This other guard cannot see through this optical. So it's this node here. And then you set the value to be, non-empty, and then you only go through it once. So you never get to this. This other else case only happens when you get there a second time. Yeah. All right. I think it's going to be a guard. No one wants to disagree. Okay. Oh, why? Okay, so we've already selected the random free configuration. For all the components of guard, you set found to be false. For all the node, the GI, which would mean like, this node and this node, if Q belongs to the visible region of this, but it doesn't, so we just skip that. And then we go to the next node. If it's in the visible region of this, then but it's not. So we just go straight to here. Yeah. I think it's going to be a guard. No, why not? Oh, you think it's a connector? Uh, yeah, so you create an edge because it's visible by two guards. Yeah. Uh, yeah. And then you can merge different regions together. So again, I think the purpose of the merging is kind of like just to make it just to combine different parts of the space. But I mean, this is the formal way to describe it, but I feel like once you've done this once, you can kind of get the hang of how this thing would, no. You can try to do it in practice and then try to connect the different components together and the different guard. Again, the one thing that you do have to watch out for, it depends on the order of how you sample things. Because you can sample your node to be at different spots, but then your guards are going to change to a different part of the configuration space. And then what happens now is you get a very efficient path. You can get a very efficient roadmap with just 1, 2, 3, 4, 5 different components. And we can just decide, we'll try to stop here. I think the termination condition in practice might be keep trying until you hit a threshold, or keep trying until you keep rejecting so many samples that you figure you might as well just move on. Yeah. So earlier we talked a little bit about pathological cases. So those are cases that are like sort of designed to be very tricky for a robot, or they're like exam questions designed to be very, very tricky. So what happened here, like in this case, if you're trying to do a visibility-based PRM, then you might need to sample something like in this tiny region here. So another example of a pathological case is you might need to go from the start to the end here by like traversing around this area. Yeah. I think you might be able to get away with a visibility-based PRM for the second one. You might just have to be like, you would find visible region up to some portion of this narrow path, and then you would have to keep sampling. You would have to keep sampling like in this region here. So. All right. So when we've been talking about the PRM, we've been thinking about it mostly in terms of like 2D points, because it's very easy to think about that and easier to describe. So these types of algorithms, they also apply when you're dealing with more complicated robots, where Q is going to be some higher dimensional vector. You can do things like, define Q in terms of, Q being the pose of a robot or the pose of a rigid body. So if you remember from, before spring break, the pose of a rigid body consists of the translational component, or like position, plus an orientation or a rotational component. So one sort of nuance is, if you're dealing with this with higher dimensions, you may have to be careful about defining what is the difference between two different configurations, right? So what is how would you define the distance between two rigid body poses? For translation, you take their distance, I guess. What about the rotation? How do you define like the distance between two rotations? Interesting. Yeah. We'll probably talk about this in the more advanced topic, because I studied this question sometime during my prior research. So this is a question that's very interesting to me. Like, how do you define the distance between two rotations? Because you can't, like, does Euclidean distance make sense? Like, if you have two quaternions, and then quaternions are, what, again, we'll talk more about this later, but they're what we call a double cover. You can negate a quaternion, and then it gives you the same rotation. So it doesn't quite make sense to just use straight up Euclidean distance for that. So maybe just think of the function f as some abstract function that we'll cover later. If you've also heard of the geodesic distance, that's another one that people use. And when you're trying to determine the distance between two rigid bodies, what people might do is they split it up into the translational component and then the rotational component. So the distance between two rigid bodies is the weighted sum of the distance between the translation and the rotational distance. How do you pick WT and WR? You have to kind of like tune it. Yeah. So, yeah. So just keep this in mind when if you're thinking about like, how do you properly define what distances mean when we have rotations involved? So this is something I think I may cover in the second to last class in this course. That's number 27. Yeah, so this is number 17. Yeah, so other considerations for the PRM are, how do you find the K nearest neighbor to some configuration Q? So what some people often use is they use a KD tree data structure for efficient calculation. So if you haven't heard of this before, it's like a specific data structure that is supposed to be, it's supposed to be very efficient by dividing up the space, like 3D space if you're in 3D, in terms of, these are the number of, components that are within some distance to other nodes. So just look at this data structure if you want to think more about like efficient implementation. So one thing you also might want to consider are the trade-offs between your sampling density and the local planar strength. Because we talked about sampling points. So we sampled a bunch of random points. Those were all the points in the workspace. Now, you could sample more points. I mean, if it's cheap, you might as well sample a lot. Then what happens is, the denser your points become, the closer they become to their nearest neighbors on average. And so you only need a very fast planner to check for any two configurations, can you go from one to another? If your roadmap is very sparse, where you have fewer nodes, then you might need a more advanced local planner. But then, in some sense, it feels like it defeats the purpose of sampling a lot. Because if you have to have a very powerful local planner, then at the limit, it just becomes your normal planner. So you might not even, like, if the problem is such that your strong local planner can already get you from your start to the end, you might as well just use it. So I think PRM is mostly used, most practitioners will just use a very simple planner to check if two configurations are reachable from one to another, and then just sample a bunch of different points. So sampling is often cheap. Collision checking, again, depends on whatever application you're using. So you might have to make the judgment call on this. So, Right, and then you might have seen that some of our paths seem like they were very inefficient, or they could be improved a lot. So if you have your graph and you have a path from the start to the end, then it might be the case that your graph search algorithm has found some path, but maybe it's inefficient in some sense, like maybe you could have gotten away with fewer nodes, or maybe it needs to be smoothed out somehow. If you're trying to have a mobile robot that has like smoother curves instead of sharper curves, then maybe you need some kind of post-processing. We have also assumed undirected roadmaps. Maybe they could be directed. So that would be if the local planner can bring the robot from Q to Q prime, but not the reverse. I mean, usually in mobility, you can do the reverse. Maybe if your environment is such that it's harder to go from one to, it's harder to be reversible. Like maybe it results in some irreversible change, and the robot, then maybe that's not the case. So. And then the last question is something, again, more of a philosophical question. It's more like asking the question of, do you even need the full roadmap if you're only doing one query? So you might have done all this work to get your roadmap, but if you're only doing it for one query, maybe you should have just stopped when there existed any path, and then just stop making the rest of the roadmap. So. And there are also different ways that you can check collision between two opticals. So this is another consideration to pick when you're designing your algorithm. So again, if there's nothing, if there's one thing to take away from this, is that there's a ton of different ways to customize these types of sampling algorithms. So one way is the nature of the collision. So you have Q prime and Q double prime. That's the initial configuration, and then this is the final configuration. To find whether the two configurations can be reached from one to another, you could try incrementally checking for collision by going from Q prime to 1 to 2 to 3 to 4 to 5, and then you set your collision checker tells you that it's in contact with this optical. So after 5 collision checks, you're done. If you do it in a subdivision manner, you might start from here, and then you do some kind of binary search procedure to go from the center, and then you go to the center of the different components that are formed from it. And then here you might get 1, and then 2, then 3 here. And so after 3 queries, you return a failure. So in this case, the subdivision was more efficient. So this is just a small note about, this is actually an example of how you might do your local planner thing that we had talked about. So the local planner that tells you, can you go from, get some starting configuration to some other configuration. This kind of thing, I guess it's more useful if the nodes are kind of like close to each other, because if if it's further away, you might have to do a lot of these checks. So you may only want to do if your nodes are like close enough to each other. Yeah. Then another consideration, again, is post-processing that we talked about. So this is one option. So given our path from PRM, you could try to simplify it by greedy search. So this original path is the dashed line here. And what is happening is you can start from the initialization. Instead of going from here to the next pose, to the next configuration, you can try checking, can it go to any of the breadths? And then for the furthest that you can go, you just set that to be the next pose that's part of the path. Same thing here. Instead of going from here to here, you check all the nodes after this, and you can see if you can go from your current node to any node that's further. And then by repeating this process, you can sort of greedily find a more efficient path. Now, whether that's better or not, like if you value being in fewer nodes, then sure, it's more efficient. All right, any questions on this? All right, so today we covered what is motion planning. We covered vertex cell decomposition, as well as things like the visibility-based thing where you can go to your optical, and then you have points on it, and then you use that to make your graph. So that depends on your explicit representation of the optical. As well as the robot, we usually assume a point mass, but if it's like a mobile robot where the radius, then just increase the size of the optical. We talked about probabilistic roadmap that forms a roadmap, and then you can use it for many queries. And then it sort of abstracts away the representation of what are the obstacles, what are, and so on. And then you just defer that to the collision checker. Coming up next is another lecture on motion planning, so that's going to be RT. So I will see you on Wednesday then. All right.